All right, so let me begin here. Snow has gotten in the way again, but that's okay. Let's see here. So the question is, suppose we have a basis beta, and here's the notation I'll use in today's lecture: v1, v2, vn. All right, but for vector space over a field f, right? But suppose you also have another basis, beta bar. So put bars over it, right? Then the question is, if we take a particular vector, right, and we say x is equal to, well, on the one hand, it's, c1 v1 plus cn vn. And we can also expand it in terms of the other basis, right? Let's see, c bar 1, v bar 1 plus c bar n, v bar n. The question is, how, so of course we have in our usual notation, x beta would be c1 through cn, right? X beta bar would be c bar 1 through c bar n. And the question is, how are these related, right? If at all. Well, in fact, they are. And the answer comes simply to us from just a little picture. So let's see here. If we think about this being the vector space, V, right? Well, on the one hand, we have phi beta, right? On the other hand, we have phi beta bar. So I can picture two different copies of Fn down here. It's just convenient for the purposes of my picturing. And so on the one hand, on the one side, I've got the, so up here is x, right? So here we have the beta coordinate vector. Over here we have the beta bar coordinate vector. And how do you get from one side to the other? Well, pretty simple. To get from here to here, we take this path like that, right? So what is that path? That path is phi beta bar, last comes first, remember, for composites. Phi beta bar composed with phi beta inverse. And so there you have it. In particular, we have that phi beta bar composed with phi beta inverse. All right, that, if we let that act on x beta, we will get x beta bar. And so, of course, this mapping I just talked about, this is linear transformation from Fn to Fn, right? Or I could just use this. I mean, it's a linear transformation on Fn for what it's worth. The point is that we can write that in terms of its standard matrix. So we have the following: the standard matrix, phi beta bar composed with phi beta inverse, the standard matrix of that, times x beta is equal to x beta bar. So this right here, so this what I'm about to do is definition. The definition that I'm talking about is to say that it's the coordinate change matrix to go from the beta basis to the beta bar basis. So there's a bit of notation for you. Let's see here. I mean, if you're like, well, you just drew this picture, that's not really a proof. Oh, okay, fine, fair enough. But let's see here. What do we say? Phi beta of x is equal to x beta, right? And phi beta bar of x is equal to x beta bar. All right. So how do I get from one to the other? Well, let's see. Phi beta bar is equal to, well, phi beta bar composed with phi beta inverse composed with phi beta, right? So I just did what? I just inserted, this is nothing more than the identity. on the vector space that's in consideration identity on V. See, because basically we're going V, the first copy of the phi beta does first, right? That takes me to Fn, and then phi beta inverse takes me back to V again. So that's the identity on V. I just inserted it. So this is an identity. That's just a tautology. And then if you feed that, right, X, ooh, exciting. That, by definition of what's going on here, that's phi beta of X, right? And so that gives us that the coordinate vector of, uh-oh, looks like this video will be coming to a close soon. X beta bar is equal to, then this is a linear transformation, so I can rewrite this as the matrix of that, like so, times x beta. So there you go, there's the derivation of the coordinate change formula right there. So when I pick this back up, I'll try to work maybe a pair of examples for this, and we'll talk about how this specializes when we're looking at the case that V is column vectors. Anyway, I'll pick it up again here in a little bit. Thanks, guys.